Okay, today we will be focusing on question 4 from the 2016 exam. I've classified this question as a type 6 question because it has to do with slope fields and differential equations. This particular one is no calculator. And most of these problems are pretty much the same in the sense that we start off with doing a slope field and then we find particular solutions to differential equations. Sometimes they throw in a little bit extra to the problem, as we have in this case. So first off, slope fields. We want to sketch the slope at these 6 points. Notice there's no points located at x equals 1, and that makes sense because if we plugged 1 in for x, we would get the divide by 0 error, which means the slope is undefined everywhere where x equals 1. So we're not going to draw the slope there. So as a quick refresher, the way we calculate slope is we pick an arbitrary point, like we'll say at 2, 1. So 2, 1, we're looking for the slope at this point, and we stick that into our slope generating equation. So 1 squared over 2 minus 1 is equal to 1 over 1. So at this coordinate, we draw a slope of 1. We'll do that one more time for our second point. dy dx at, we'll go this time 2, 2, 2, 2. And plug 2 in for y, 2 in for x, and we get 4 halves, or a slope of 2. And just for the sake of learning, we'll throw one more in there, dy dx at 2, 0. So 0 squared over 2 minus 1 is equal to 0 1/8. I made a mistake there. 2 minus 1 is 1. Okay, so slope of 0 over 1 is 0, so we draw a 0 slope there. If we continue doing that for all 6 points, 1, 2, 3, 4, 5, 6, this one has a slope of 0, this one has a slope of -1, and this one has a slope of -4. So 4, -4, 1, -1, 0, 0. Okay, this is worth 2 points. The first point comes from having the 0 slopes correctly. So if you had your 0 slopes correctly, you'd get a point there, and then the non-zero slopes, what they're going to look for is, do we have this slope being relatively steeper than this one? Both of these are positive. And this slope is relatively steeper than this one. Both of these are positive. So 2 points for the slope field part. All right, let's move on to part B. Let y be f of x, y equals f of x be the particular solution to given differential equation. They give us an initial equation. Write the equation of a line tangent to the graph. So we're doing our tangent line approximator. This is old school, very basic, start of calculus class. Our function can be approximated by a tangent line, which we let be equal to f of the center plus f prime of the center times x minus the center. And in this case, our center is at 2, so we're going to plug 2 in for the c. So f of x is approximated by L of x, which is f of 2 plus f prime of 2 times x minus 2. F of 2 they give us. F of 2 is 3. So f of 2 we replace with 3. And then f prime of 2, this is asking what is the slope at x equals 2, more specifically at 2, 3. So off to the side, we're going to find what is the slope at 2, 3. And we get 9 over 1. So a slope of 9 times x minus 2. So this is the first part, which says write the equation of the tangent line. And that is going to be worth 1 point if you found the tangent line approximator. And then the next point comes from using that to approximate f of 2.1. So f of 2.1 is going to be approximated by the line at 2.1, which is 3 plus 9 times 2.1 minus 2. And this is numerically equivalent to the answer, or the approximation, so we can stop there. If you were one of the individuals who continues cleaning this up, this simplifies down to 3.9. And you get your second point for finding that approximation off of the tangent line equation. Okay then, let's do part C, finding the particular solution. So this is where the separation of variables comes in. And we have dy dx is equal to y squared over x minus 1. So step 1 is to separate the variables. So I'm going to divide y squared to the left and multiply dx to the right. So there's our separation of variables. Plus 1 if you correctly separated the variables. From there, we want to take the antiderivatives of both sides, or find the antiderivatives. And the antiderivative of the left is negative 1 over y, and the antiderivative of the right requires the use of u substitution, but because our denominator is linear and a leading coefficient of 1, it's pretty safe to do the logarithm like that. You have the addition of the constant on both sides. I will merge them into the constant on just the right-hand side. This here is worth 2 points. You get 2 points for the antiderivatives. Now, from here, we want to use the initial condition to start solving for what is this value of c. So when y is 3, x is 2. So negative 1/3 equals ln of 2 minus 1 plus c. So c is equal to, well, we see here ln of 2 minus 1 is ln of 1. The natural log of 1 is equal to 0. So we have negative 1/3 equals 0 plus c. So c is negative 1/3. Okay. So you get your next point if you use the constant of integration and the initial condition. So 1 point for using the constant of integration and the initial condition. And then finally, we need to solve this for y. So if we go back to negative 1 over y, we can start solving this for y. So let's see. We can multiply y to the right-hand side. And then divide the non-y terms to the right. And this is equal to y. Find the particular solution. So we've got to our particular solution, plus 1 for that. Okay. All in all, this is a pretty straightforward problem. There wasn't a lot of difficulty in solving for y, or the constant of integration, finding that value. No heavy lifting on the algebra, but pretty straightforward. Typically, this part is worth 5 or 6 points. Very commonly, 1 point for the separation, 2 points for the antiderivatives, 1 point for the constant of integration, and sometimes they give you 1 point for plugging in the initial condition, and then 1 for the final answer. So, and then in general, the slope field is usually worth 2 or 3 points, and then the extra thing they throw in there, sometimes one, sometimes 2 points. All right, thanks for watching. Be sure to comment, like, and subscribe. Have a good day.